And there's this somewhat complicated interplay between the particles and wave activity, electromagnetic wave activity in the region, which causes this acceleration. Now, this is not a focus of my talk, so I'm not going to go into a lot of details of that. I refer to the diagram on the bottom left here from Alison Janes, which tries to explain this process of energization. But it is somewhat complicated, of course. So on the other side, after, oh, sorry, I want to get into particle losses next, but to do that, I'm just going to quickly give a brief overview of the particle dynamics in the radiation belts. I like to give this is a compressed version of some slides that I teach when I teach particle motion in one of my classes. We have three main motions of energetic electrons in the near-Earth space environment, in the Earth's magnetosphere. There's the gyro motion, where an electron gyrates around a magnetic field line. There's the bounce motion, where these particles, you see them bouncing back and forth along, sorry, I'm trying to get the movie to go again. The particles bounce back and forth along the field line from one hemisphere to the other. Movie's not going again, is it? And then there's the drift motion, where these particles slowly drift around the Earth in the azimuthal direction. So I've sort of diagrammed each of those motions on the top right, and then given you approximate time scales for the drift around the Earth, which can vary from seconds to hours, depending on energy and the distance from the Earth. All of these motions are driven by the Lorentz force, as well as the configuration of the Earth's magnetic field. So that kind of ties into the discussion of particle losses from the radiation belts. How are these particles removed from the radiation belts after a major enhancement? And there's two processes that we largely focus on. The first is magnetopause shadowing. This is the process by which these particles, as they're drifting around the Earth, so they're doing that drift motion I just talked about. The diagram here on the top right shows you a conception of what happens. These particles are drifting around the Earth, and during a geomagnetic event, the magnetosphere is compressed, and the magnetopause, which is the boundary between open and closed field lines, can be pushed inwards closer to the Earth. And so particles that are drifting around the Earth on the night side, when they reach the day side, they'll reach open field lines and be lost to space. So that's the basic concept of magnetopause shadowing. I really like the graphic on the bottom right from Yu et al., which shows simulations and data of a magnetopause shadowing event. So again, we're looking at L shell on the y-axis, phase space density for the two leftmost of the four-quadrant plot, and then time in days, plus or minus 3 days on the bottom, where 0 is sort of the nominal event time. And so you see this significant depletion in the phase space density, which is equivalent to sort of a particle flux, right around t equals 0. What's particularly interesting about this is that the particle loss is not just from the magnetopause boundary, which is up there at L of 7 or 8. Particles are initially lost from those high L shells, but then due to radial diffusion, particles at the lower L shells will then be pushed to higher L shells and ultimately get lost out that boundary. So at least it was an early misconception of my own when I was first learning about this. How do we lose particles from L equals 4 by magnetopause shadowing? Well, it's this radial diffusion which will push particles out as they're being lost at the far end of the pipe. So this is one of the loss mechanisms, and there's plenty of research going on this concept, which is, again, not the focus of this talk. The focus of this talk is on the other loss mechanism, which is precipitation. So in a general sense, precipitation is the concept where particles are lost to the Earth's upper atmosphere by collisions with the neutral atmosphere. And I'll get into the details of that in a second. So coming back again to the particle motions that I talked about 2 slides ago, the bounce motion is this process by which particles are bouncing along a magnetic field line from one hemisphere to the other. It's driven by the first adiabatic invariant and conservation thereof. And particles have what's called a pitch angle. And so that's the angle between the spiral that they're making around the Earth's magnetic field and the magnetic field line itself. A higher pitch angle means that a particle will, well, a lower equatorial pitch angle means that a particle will mirror at a lower altitude. So the diagram on the left shows you for an equatorial pitch angle of 10 degrees, meaning the angle between the particle's spiral and the magnetic field is 10 degrees at the equator. Those particles can reach all the way down to the Earth before they are essentially reflected by the Earth's magnetic mirror force. Higher pitch angles will mirror at higher altitudes. So at a equatorial pitch angle of 35 degrees, you can see that that particle is making it nowhere near the atmosphere. And so that particle is going to be stably trapped in the magnetic field. Now, the concept of precipitation is that these particles are somehow being kicked, they're being pushed by some force in the radiation belt environment to a lower pitch angle. And as they're pushed to a lower pitch angle, they can then penetrate into the atmosphere. And if they do so, if they can reach nominally an altitude of about 100 kilometers, then they face a high probability of colliding with a neutral molecule in the atmosphere. Because the atmosphere density profile is exponential, you end up with a fairly sharp boundary at 100-kilometer altitude. So there is some probability, which depends on altitude, but it goes from a probability near zero at 120 kilometers to a probability close to 1 at 80 kilometers. And so it's a very, very, very sharp loss boundary. We refer to this, by the way, the range of pitch angles which can reach that altitude, we refer to as the loss cone. You'll see me talk about the loss cone a few times later on. The diagram on the right kind of shows you where we then expect most precipitation to occur. These particles will penetrate into the atmosphere and, again, be lost by collisions with neutrals and deposit their energy. And we'll talk about the various ways that they deposit energy in a second. But depending on the type of radiation, as well as the energy for electrons and protons, for example, they penetrate to different altitudes. And so this process of precipitation is relevant to radiation belt electrons. That's the red band in this plot on the right, but also solar protons, auroral electrons, and solar photons. And so this is highlighting how each of those different constituents deposit into different altitude ranges of the atmosphere. For these radiation belt electrons, we're mostly going to see the effects between 50 and 100 kilometers, but we will see effects even lower than that, which I'll talk about as well. One other quick sort of side concept that I have to introduce for the students is the concept of the bounce versus the drift loss cone. The Earth's magnetic field is not symmetric in longitude. And what that means is the loss cone, the range of angles that will precipitate, is different at different longitudes. The extreme case is at the South Atlantic anomaly, which is just over the South Atlantic Ocean. And what that means is that particles that are not in the loss cone, not quite in the loss cone at other longitudes, they will drift around the Earth in the same drift motion I talked about before, and they can reach a longitude where they are in the local bounce loss cone for that longitude. And ultimately, they will all reach the South Atlantic anomaly, and that's where the most particles are going to ultimately precipitate. So we refer to these particles that are not in the local bounce loss cone, but are in the South Atlantic anomaly's bounce loss cone. We refer to those as quasi-trapped particles or particles in the drift loss cone, because they will ultimately drift into the loss cone and be precipitated. The important takeaway from this is that particles actually only need to be scattered into this drift loss cone to ultimately be precipitated into the atmosphere. They might not be scattered into the local bounce loss cone, but if they're scattered into the drift loss cone, which is a single value around the Earth, they can still be lost. So what happens to particles when they precipitate in the atmosphere? Well, they cause ionization first and foremost. We're talking about, again, hundreds of keV to MeV electrons. It only takes about 35 eV to produce an electron-ion pair in the Earth's atmosphere. And so a single electron can actually produce thousands of pairs of free electrons in the upper atmosphere. This means it temporarily modifies the D region ionosphere. The 50 to 100 kilometer region is really the D or lower E region of the Earth's ionosphere. So it's adding to the ionization in the ionosphere. The highest energies reach lowest altitudes, lower energies reach, that's supposed to say higher altitudes. And again, the main effect there is the direct impact ionization of N2 and O2. There are further effects that I'll talk about in a second. Yeah, in particular, this ionization produces N2 plus and O2 plus, and then there's a complicated chemistry which will lead to other interesting molecules being enhanced. And in particular, we care about NOx and HOx, that's NOx and HOx, which are things like NO, NO2, HO, HO2, and so forth. So this D region ionosphere that I mentioned is a region that any of you who study the ionosphere probably ignore. It's the lowest altitude region of the ionosphere, the very bottom shelf. The densities are very, very low compared to the E and F region, 1 or 2 or more orders of magnitude lower than the E region. The altitude region we're typically focused on for the D region is 65 to 90-ish kilometers. It tends to be higher and less dense at night for semi-obvious reasons. The D region is produced largely by solar ionization, Lyman alpha, and solar EUV. And so when the sun goes away, the D region relaxes. The D region is particularly known, though, for the complex cluster ions that exist in this region. And those end up leading to, as I said, a complicated chemistry. This plot that I'm trying to show you on the bottom right, the 2 plots, are a reduced chemistry model for the D region ionosphere, highlighting just some of the main constituents and really just trying to show you how complicated all the various chemistry pathways are. So the ones highlighted in blue are kind of the main constituents that we are concerned with. And there are even more reduced D region dense chemistry models which only use those blue molecules. And then in the green and white, they're adding in a lot of more complicated chemistry. And so it highlights some of the complexity of understanding and modeling the D region and how it responds to energy inputs. The D region also reflects VLF waves, and I'll talk about this in terms of a different diagnostic technique in a second. And it's important because it absorbs HF energy. So it has effect on long-range HF communications. Now, this is a little outside of my research. I'm really pointing here to Cora Randall, one of our co-investigators, and other colleagues in the upper atmosphere community. But the focus here is on the effects of NOx. NOx is a set of molecules which has important effects in the upper atmosphere, one of which is being destructive to ozone. NOx can be created in the mesosphere or in the lower thermosphere. And it can then, in the absence of sunlight, it can actually last a very long time and descend to the bottom of the mesosphere and into the stratosphere. And then when it reaches ozone, it'll actually reactively destroy ozone. So models have worked very hard for many years to reproduce observed NOx densities by comparing to spacecraft measurements going back some years now. And the 2 figures that I've got here are kind of trying to highlight the difference between observations and models. So the lower left from Cora Randall's paper shows you observations of NOx from MIPAS, the MIPAS instrument. And then the center panel is a simulation from the Wacom model, which all of you, I'm sure, are familiar with. And then the third panel, of course, is the difference. And so even without looking at the difference plot, you can see that there is a huge and significant difference between the model and the observation. Same thing on the top right. This is slightly newer results. Looking at the MIPAS data on the top left of these 9 panels. And then each of the other panels is a model reproduction of the response of what was observed. And they've overplotted the white contours, which are from the MIPAS data, to show you the differences between model and observation. So critically, there's a significant difference between model and observation. And for the last few years, the discussion has been over what is missing from the model that produces this difference. The two main possibilities are an incorrect parameterization of the precipitating particles. So that really points to the need for better measurements, or an incorrect modeling of transport, vertical and/or horizontal transport. And so that really becomes more of a modeling question. So we're obviously focused on the first one, which is improving that parameterization of the particle inputs. So we can look at a number of different ways. I came to this community and this project from mainly the VLF and optical regimes, where I used to do most of my research. Still do a lot of VLF, of course. And I came up with this diagram which tries to highlight like all the possible signatures and effects related to this electron precipitation into the upper atmosphere. So at the top, the precipitation, given a flux and energy spectrum, produces ionization, produces X-rays and gamma rays, I'll talk about in a second, also produces backscatter. And then those lead to chemistry, change in electron density, optical emissions. And then the sort of colorful row there is looking at all the possible diagnostics that we could use to estimate this precipitation. So ingesting all of this information from all of these observations would somehow go into this magical green box at the bottom, the data-driven model inversion, and produce a perfect estimate of precipitation. This, of course, was somewhat far-fetched to put all of this into one model. So I just want to talk about some of these methods, though. And some of these we're working on in other projects. So one possibility is looking at sub-ionospheric VLF, that pink and green box in the middle of the diagram. We're designing now, and I have proposed, an array of VLF receivers over Canada, which monitor narrowband VLF transmitters in the US. And we can take the measurements from those receivers and through an inversion model, estimate the state of the D region ionosphere. That'll give us the ionosphere profiles in a two-dimensional grid as shown. And from that, we can infer the actual precipitation fluxes that produced that ionosphere. So the topmost panel here kind of shows you that this is kind of sort of working a little bit. Another method, of course, to look at the precipitation is to look at the actual fluxes that are lost from the radiation belts. And so we've been trying to do some comparisons between medium Earth orbit satellites like Van Allen probes on the top and GPS satellites, which also have energetic particle detectors, and low Earth orbit satellites like POES. POES, by the way, is the input that's commonly used as the parameterized source for the Wacom model, for example. And so we're looking at comparisons between what's lost from the radiation belts and what's measured in LEO to try to get them to line up. We are working on a new project just starting now where we're actually going to combine POES observations with the Iridium constellation. The Iridium Next constellation has radiation dose detectors on each spacecraft. I'll talk about that actually in another slide shortly. And that'll give us a larger two-dimensional view of, three-dimensional view really, of what the input to the atmosphere looks like. Another method is using ground-based radar, which you might have seen on the diagram behind this. We have done quite a bit of work with the Pfizer radar, which is up in Alaska, by measuring the electron density profiles in the D region. Our colleagues at SRI have vastly improved a method of measuring D region density profiles. It's very difficult because, again, those densities are very, very low. And then we do a forward model given a assumed precipitation and flux and spectrum and try to get it to match the radar observation. So far, the match has not been spectacular for reasons I won't get into today. So those are kind of some of the methods that we could use and or combine to improve these measurements. They're all very complicated. There's been quite a bit of progress on the direct measurement method. So taking POES data, obviously the most relevant method is to just measure the particles that are entering the atmosphere. It's challenging though, because any instrument has a limited electron detector field of view, as well as limited spatial and temporal coverage. So you can't get a perfect measurement. We're working with Hilda Nessa-Tissoy, who's been doing some nice work where she takes the measurements from POES in its 2 detectors and fits the most likely pitch angle distribution of those electrons. And then we can forward model those to get a better estimate of the ionization impact in the atmosphere. And I'll quickly mention a postdoc working with me, Wei Zhu, has developed a new parameterization method, sort of a lookup table, where given an electron flux and spectrum from any satellite and a pitch angle distribution, and assuming any atmosphere density profile, this is essentially a lookup table that will spit out the ionization profiles. And we can use that. It's much, much more rapid than doing full Monte Carlo modeling, for example, to get the ionization inputs that go into chemistry models such as Wacom. So the other effect that I didn't really mention a couple slides ago then is Bremsstrahlung. And this is really where we're focusing with APEX and with this talk. So this diagram is kind of highlighting all of these effects, diagram that I put together a couple years ago, and effects and observation methods. And the squiggly yellow lines there in the middle are X-rays produced by the atmosphere. So this has now evolved into this diagram where we're really focusing in now on these, I forgot about that fire transition, I didn't know that was there. We're looking at these X-rays. So the basic picture again is energetic electrons come down the magnetic field lines, collide with the atmosphere, and then through this process of Bremsstrahlung, they produce X-rays. And X-rays give us the opportunity not just to make an indirect measurement of this precipitation, but also to image it over a much larger region. So my very quick requisite overview of Bremsstrahlung. Bremsstrahlung is when an energetic particle, such as an electron, passes very close to the nucleus of an atom. The positive charge of the nucleus causes an acceleration of that electron. And in order to conserve energy and momentum, a photon is emitted. This is the quadruply differential cross-section for Bremsstrahlung. I don't know why I put this into my talks. I did this a couple years ago, and it's kind of ridiculous. Just to show how complicated it is, I guess. Well, I'll give you the takeaway. The point is that the calculation of Bremsstrahlung, which is to say what energy of photon is produced for a given electron, and at what angle is that photon emitted, that depends on the atomic number of the molecule that is accelerating it, such as N2. And it depends on the initial and final electron energy and initial and final electron momentum, as well as the photon, the wavelength or frequency of the photon that's produced. So this is the cross-section. Here it is expanded into a simplified equation, the equation on the right there. This is converting it into something that's implementable. And there's a nice assumption here, which is that we don't care about one of the emission angles, considering that it's two-dimensionally symmetric. So this is now just a doubly differential cross-section. And you can take this ridiculous equation and plot it to get the plots that I've got here on the bottom right. And they provide some of the useful information that we need to know, basic information about Bremsstrahlung that's kind of useful. For example, that the cross-section is significantly higher with lower photon energy. That's what we're seeing on the left here. That means we produce many, many, many more photons at 1 keV compared to photons at 100 keV, pretty much irrespective of the initial electron energy. So you can take a line somewhere on the x-axis, let's say a few hundred keV, and you'll notice that we only produce a few of those hundreds of keV secondary photons, but orders of magnitude more low energy photons. Then the plot on the right of the set here shows you the sort of the angular distribution of that cross section. And the takeaway from this is that the angular distribution becomes more and more focused with higher electron energy. So the different curves are for that initial electron energy. At 1 keV, it's kind of a peanut shape that's otherwise almost omnidirectional. So photons are being radiated in all directions. And then when you get to 10 MeV, you have a very, very narrow focused beam in the same direction as the initial electron. And so the plot on the right shows you that full width half max of that radiation main lobe, where it goes down to single-digit degrees for the very, very high energies. That means that an electron coming down the magnetic field line in a straight line, very high energy electron, if it produces high energy photons, they will continue in the same direction as the electron. And so that kind of relates to the next process here. I'm going to jump quickly to the plot, the altitude versus ionization rate shown here. And you see 3 different plots, and each of them kind of has a double peak. The first peak at higher altitudes, if you look at the black curve, which is 100 keV electrons, there's a first peak at about 80-ish kilometer altitude. That's where most of the ionization is produced by the precipitating electrons, when they just simply produce electron-ion pairs. But they produce photons as well through Bremsstrahlung. They produce photons in that altitude range where you're seeing that initial ionization. But those photons can continue to propagate deeper into the atmosphere. They have a smaller collision cross-section with the atmosphere. So they penetrate deeper, lower in altitude, and deposit their energy all the way down to 20 kilometers or even lower, depending on the photon energy largely. So as a rough rule of thumb, you can calculate the total amount of energy that will be converted into X-rays. It's about 2% at 1 MeV and kind of semi-exponential with electron energy. And that'll give us a rough idea of how much extra ionization we produce at these lower altitudes. Now, we do all this in a full Monte Carlo model to get the detailed numerical calculations of how much ionization is produced by Bremsstrahlung. Now, the fact that this ionization is produced at these low altitudes gives the opportunity to measure these X-rays from high altitude balloons. A lot of this ionization is below 35 or 40 kilometers, and that's kind of the approximate altitude for high altitude balloons. So there have been a number of missions going back decades that have made these observations. This is nothing particularly new. The most recent, of course, is Beryl, shown here on the right. And Beryl is a series of dozens of balloon missions that have flown over a number of years, complementary to Van Allen probes, in fact. And they've made just some fantastic measurements of radiation belt precipitation through these X-ray signatures. Now, I want to quickly highlight something that's kind of interesting. If we do, they're pretty unusual, but if we get extremely high energy electrons, like these 10 MeV electrons, and there's enough of them, if you follow that red curve down, the bottom of that curve of ionization is below 10 kilometer altitude. And if you've ever been in a plane and you can convert kilometers to feet, I don't think I can. 10 kilometers is about 30,000 feet, roughly. So these are at aviation altitudes. And measurements have actually been made that are potentially indicative of radiation belt precipitation. So I'm pointing largely to Kent Tubiska, who's been collecting data in this regard for quite a number of years now. And the plot on the top right is his data. The black and red curve there is approximately a fit to the radiation dose that we would expect from galactic cosmic rays, GCRs. And then the dots, and especially the black highlighted dots above that, are some extreme measurements that have been made by these flights. And so we're seeing a factor of 2 or more increase in radiation dose. And it seems to be particularly concentrated between L shells of about 2 and 6. So that has led Kent to suggest that this increased dose is from radiation belt precipitation. And then I randomly saw him give a talk on this at the American Meteorological Society meeting, and showed him some of our simulation results of this low altitude Bremsstrahlung. And so we have since gotten together. We wrote a proposal, and we're actually selected from the NASA Space Weather Operations 2 research to use our modeling plus his data plus low Earth orbit electron data from both POES and REACH to tie these things together. and really answer the question if is what they're seeing at these high aviation altitudes, is that really radiation belt precipitation? And if so, can we provide some information on when to expect these enhanced radiation events? I said REACH. REACH, by the way, is the name of the instrument on the Iridium NEXT constellation. So again, Iridium NEXT has 60-something satellites. About half of them carry this radiation dose monitor. They won't give us an accurate flux. They won't give us an accurate spectrum, but they will fill in a very detailed two-dimensional map of radiation. And we can then scale that with POES data, which does have flux and spectrum, to give a really good picture of the input into the entire Earth system from the radiation belts. Okay, so that was a bit of a sidetrack. I'll jump back into what we're talking about. Here's just some examples of X-ray data, spectra observed by Beryl associated with radiation belt precipitation. So I'll just point you to the figure on the bottom left and the highlighted region there that says precipitation. And this is kind of what we see, what is seen from these high altitude balloons, and a significant order of magnitude or more enhancement in the X-ray flux between about 100 keV and up to an MeV. The complicated part about this type of measurement, of course, is we have to, given the measured X-ray flux and spectrum, how do we invert that to infer the electron flux and spectrum? And that is a challenging problem, and I'll say a little bit more about that in a couple slides. So this kind of jumps us now into APEX in this mission. And I just list here kind of as a summary of everything I've said so far, the science questions associated with APEX. We want to understand how much energy is deposited into the upper atmosphere through energetic particle precipitation, EPP, and look at its variation with time and geography. And then the other question is, what is the spatial scale of these precipitation regions? The other measurements that I showed you, direct electron measurements, as well as the balloon X-ray measurements, are basically single point measurements. And so they can't really give us a sense of spatial scale. The inputs into the Wacom model, for example, to look at the global effect of this precipitation requires an estimate of the geography of these precipitation events as well. So the way we're going to do this on APEX is to measure the flux and spectrum of precipitating electrons, boring, as well as measure the spatial extent of these precipitation regions with roughly 200-kilometer resolution. And I'll show you how we're going to do that. Okay, so here's our approach to this problem. I mentioned this already, that the direct particle measurements are great, but it's difficult to get the accurate flux without a really accurate pitch angle distribution measurement, and there's no spatial information. So by measuring the X-rays backscattered from the atmosphere, we can, number one, we can image them and get a two-dimensional view of the spatial extent of these events. But also the X-rays that are measured are directly indicative of electron precipitation. We know that any photon emitted comes from an electron which actually hit the atmosphere. Whereas with the particle measurements, again, without the accurate pitch angle distribution, you never quite know if you're measuring everything that's precipitating or if you've got some electrons that are going to mirror or be backscattered or so forth. I mentioned complications here. As I said, the inversion from X-rays to particles is difficult, and I'll say a bit about that in a second. We have sort of overcome that by adding a particle detector to the instrument, which will directly measure the electron spectrum fairly accurately, even if it can't get the flux extremely well. As a programmatic thing, APEX, this mission has been proposed, was proposed 3 times before being selected, was finally selected by NASA in the H-TIDES call in September of 2019. So that was when we came out of the concept study. And so we entered phase B, and development has really started just in the past year. So I'll quickly say something about this inversion. I'm showing you some plots here, and I will highlight, well, I can't highlight with the mouse. If you look at the first column of plots, the 3 on the left, those are showing you the simulated photon distributions, energy distributions. At the top two are at the satellite altitude for two different precipitating electron distributions, and the bottom is a balloon distribution. The tricky thing about this inversion is that that photon energy distribution does not strongly depend on the electron energy distribution. They look kind of the same for two different energetic electron distributions. So it can be very difficult to make that inversion because these distributions only vary ever so slightly. Nonetheless, again, Wei Zhu, the postdoc working with me, has done quite a bit of work to attempt this inversion and show that it's feasible. So these plots are showing you, again, on the left, the photon distribution that we would measure. On the right, sorry, on the center plot, it's showing the inferred electron distribution in the color plot with error bars on top of the actual energy distribution. So it's doing a reasonable job of inferring that distribution. And then on the right is we forward model both the true as well as the inferred electron energy distribution to get the atmospheric ionization response. And we can see how different they are from the based on the truth as well as our best estimate, and including the error bars on that best estimate. And we find about a 20% difference, which is pretty good, I think. This type of inversion is not new. We didn't invent this method. Robin Millen and various others have applied this to the barrel data. The only thing that we've done new is apply it to measurements at satellite altitudes. Now, this was done early on before we added a particle detector. When we decided to add a particle detector to the mission, we updated this inversion method to be constrained by the electron energy distribution. And without going through all these details of how the whole process works, the takeaway is that we now get 10 to 20% error, both on the inferred precipitating flux as well as the atmospheric ionization profile based on our simulated measurements. Okay, now I will really get into APEX. So APEX is a low Earth orbiting mission in a high inclination orbit in order to reach radiation belt latitudes. So we want an inclination of at least 70 degrees so that we're constantly going through the radiation belts. The choice of altitude has some range, but there's a trade-off. If we go to a higher altitude, we have a larger field of view, which is good, but reduced flux and spatial resolution, which is not so good. It's going to be a circularly orbiting mission. The basic CONOPS is the little movie on the bottom right, which I can see is kind of choppy on the streaming video, is showing you the basic satellite orientation and how the CONOPS is going to work. So the mission is, the yellow vector there is pointing at the sun, and then the green vector is pointing at nadir. So when the mission is above 40-degree latitude or below negative 40-degree latitude, i.e. in the radiation belt regions, it will be nadir pointing. So the imaging instrument is looking directly down at the Earth. And then when we're in the moderate mid-equatorial latitudes and there isn't really anything to measure, we rotate the spacecraft to point at the sun to charge solar panels. On the day side, of course. So that's a really simple, basic mission CONOPS. We'll be using the ground station here in Boulder at LASP. I'm sure you've all seen it, to downlink our data and so forth. And this is a 6U CubeSat, if that was not already obvious. It's a relatively heavy CubeSat. It's one of the issues and risks that we are constantly paying attention to in the development. And it's also a power-hungry CubeSat. And I'll comment on both of those things shortly. So I talked about the CONOPS already in terms of the orbit. So this plot on the top right kind of gives you a sense of our desired as well as preferred orbits. So the red region there would be, with an inclination of 70 degrees, we would be taking data in that red region of the map. If we can push that inclination up to 80 degrees, we get the green region as well, which gets the radiation belts over the Antarctic Peninsula area. To give a quick sense of what we expect to see, there will be times when we don't really measure much of anything, when there isn't a radiation belt enhancement followed by a depletion. But we use POES data to kind of estimate the number of events we can expect over a 1-year mission lifetime. And so we looked at the POES data with greater than 100 keV electrons in their 0-degree detectors. So those are electrons that are definitely precipitating in the atmosphere. And we set a flux threshold to say when there's a new event and make them non-consecutive in days. And the sort of bar chart, quasi-histogram thing on the right, stem chart, I guess, gives you a sense of the number of events we can expect in a given year. And there's clearly a solar cycle dependence there with a minimum in 2009. And so if we launch in 2022, we'll be kind of on the ascending phase of the solar cycle and hopefully get a couple dozen events at least. So here's what the missions and spacecraft instruments look like. There's 2 instruments on this mission, AFIRE and AXIS. AFIRE is the particle detector. It's very creative naming. FIRE is the instrument on the Firebird CubeSat developed by UNH and University of Montana. And so AFIRE is the Apex Fire instrument. It's a built-to-print copy of the instrument on Firebird. And then AXIS is our novel X-ray imaging instrument, which I'm really going to spend some time telling you more about. So a quick overview of AFIRE. Again, this is built to print from Firebird. It covers electron energies from 200 keV to 1 MeV, so avoiding anything that could be considered auroral electrons. We can get a pretty good energy resolution with this instrument. We can software define the number of energy bins to get a distribution. On Firebird, they only used 6 energy bins, so they didn't have great resolution. That was largely due to a data downlinking limitation. And we'll record at a time resolution of about 1 hertz. The instrument has 2 detectors. There's what they call the surface detector, which has basically a 2 pi steradian field of view, so it's omnidirectional. And then a collimated detector with a narrower field of view focusing on electrons in the loss cone. And this whole instrument is half a U in volume, so 10 by 10 by 5 centimeters, and uses about 1/4 watt of power. Now, AXIS is our newer novel instrument that we're developing for this mission. AXIS is an array of 12 cadmium zinc telluride detectors. These are shown on the right. These are detectors from a company called Redlen. They're designed for medical/security X-ray imaging, and we are repurposing them for space science. Each of these detectors measures photons between 50 and 300 keV and is a 16 by 16 pixel array. Chris Cully, who's a co-I on this mission at University of Calgary, developed the first version of this instrument with this detector and flew it on some high-altitude balloons, proving that they can work in a cold, tenuous environment, which was very helpful. The picture on the top of this slide, top right, is actually his instrument. In previous iterations, we've used a slit or a pinhole to image with this detector. We're actually developing a coated aperture for imaging. I won't get into the details of coated aperture imaging, but this is a reasonably common method of imaging in X-rays, since we can't use lenses, by using this coated mask to sort of mask, obviously, the image that's seen on the detector. And then by deconvolving the observation with the coated aperture, we can get back the image at distance. The other important aspect of this instrument is the housing. These detectors will get hit by photons from the side, and they'll get hit by electrons and protons, and they will be fooled into thinking those are photons. So we have to shield the instrument from penetrating electrons and protons from the space environment, as well as photons outside of the field of view. This is largely why this mission is heavy, because to shield photons, we have to use high Z materials like tungsten. So the housing is actually a graded Z box, meaning there's layers with progressively changing Z values. There's a polyethylene layer, a plastic layer with very, very low Z that'll absorb electrons without producing Bremsstrahlung photons. Then there's a tungsten layer, which will absorb any photons that make it through the plastic. Tungsten, though, will re-emit at about 60 keV, its characteristic energy. And so there's a tin layer inside of that, which will absorb those 60 keV photons, re-emit at about 25 keV, which is below the energy sensitivity of the detector. The figure on the bottom just shows you an example of an image that we got from the detector, as well as the spectrum of a cobalt source, showing that we're getting the spectrum we expect. I said a little bit about coded aperture imaging already. I do see that I'm running out of time, so I'm going to skip over this and not go into details. I'll just mention that Grant Berland is a PhD student working with me, and he's been doing a lot of work on how to optimize this coded aperture imaging and how to infer the precipitating source image from what we get out of the detectors. Again, I don't need to go too much into the instrument architecture here. This block diagram kind of shows you everything we've had to build just to run these detectors. And there on the bottom right is our first PCB that we built that holds 4 of the detectors. I'll highlight the image on the top right, the very colorful little box diagram. The 12 detectors are separated into quadrants of 4. And so each group of 4 work together on a single PCB and through a single microcontroller and high voltage power supply. And the data from those 4 are combined into a single histogram. The exception is in the bottom corner. There's the yellow block called the background control. We use one of the detectors without a coded aperture mask, with an opaque sheet of tungsten instead of a coded aperture. And the idea is that anything we measure in that detector, both the image as well as the spectrum of photons, is due to particles that made it through the shielding. And so that'll give us a baseline background, which we can then subtract from each of the other detectors. I'm not going to show you details, but we've done some of the modeling to show how this will work, and that background can be effectively subtracted, and we get a very nice signal-to-noise ratio then from the rest of the detectors. So effectively, we really only have 11 detectors from the point of view of counting photons. There's a team of students that is largely developing this instrument, and I've been making great progress. I really like the exploded model on the left that shows you all of the pieces that go into this instrument. This has all been now pretty thoroughly designed and simulated. The biggest issues that we're dealing with right now are, number one is the assembly. How do we put this whole thing together and make everything stay? That's coming along, as well as the thermal problem. I mentioned that this mission is power hungry. That's largely because each of these detectors consumes a little over 1 watt of power, where all told, the instrument could be as high as 20 watts when it's operating. It might not sound like a lot for those of you that don't do a lot of space mission stuff, but for a CubeSat, that's an incredible amount of power. That's leading to our very large solar arrays, but it also leads to a thermal issue where these detectors are wrapped in a big plastic box. We have to get the heat out of there somehow so that they don't overheat. Without any sort of heat sinking, those detectors will get up to 50 or 60 degrees Celsius, at which point they just become noise. They just produce an incredible amount of noise. So we have these heat straps that are designed into it right now, but there's still some work to be done both on the design of that as well as the thermal modeling to make sure it can keep the detectors in their operating temperature range. Oh, there's a movie, yes. I forgot that I had the movie in here. What you're seeing is in testing, we're moving the radiation source around in front of the coded aperture, and then in real time going through the image reconstruction, the deconvolution of the coded aperture, and you're seeing the spot from that radiation source move around the map of the image. So this is just from last week, and it's really showing that the image reconstruction algorithm is doing what it's supposed to do. Still lots of refinement, though, to get that optimized. Okay, quick overview of the spacecraft. One of the big advantages of being here at CU, again, which I'm very grateful for, is having LASP right next door, and they can do everything. LASP is developing essentially an in-house spacecraft bus architecture that will be used for current and future missions. There's a few off-the-shelf components. We buy radios from Clyde Space or other sources. We use attitude determination and control system from Blue Canyon, which has become sort of the de facto standard now. But LASP is developing their own command and data handling flight computer, power system, solar panels, software, structure, of course, and then the ground station. And so the development of this spacecraft, the takeaway is that most of that development is being done by LASP, and provides a lot of confidence that this is going to be successful, because we're not the first one that they've built. They've built quite a few in the past, actually. The spacecraft design and layout looks something like this. So we've got our nominal 6U bus. So the box is 10 by 20 by 30 centimeters, roughly. Deployable solar panels to provide about 80 watts of peak power. You know, you only get power when you're in daylight, and then you lose a little bit of power if you're not normal to the sun. So an 80-watt solar array will give us 25 or 30 watts average power. You can see, of course, where the instrument is crammed in there. The instrument and the S-band radio antenna are facing the Earth, so they would be in the nadir-facing direction. And then the AFIRE instrument and GPS antenna face the opposite direction, as well as the sun sensor. I should have added that. And then the exact and radios and electronics are all packed in there into about 2U of space at the front of the spacecraft. This is a fairly early development. We're kind of past the preliminary design, moving into critical design, which means hammering out all of the details of where everything goes and what fasteners we're using. But all of that, a lot of that detail, of course, is still to come. So speaking of which, here's where we are in the development. We, just in the past year, of course, we've had kickoff, system requirements review, PDR, and we're now charging towards critical design review. As I said, that's at the stage where we've got the design down to the nuts and bolts, as well as a detailed thermal design, and hopefully a functioning instrument. And then in 2021, we'll be building and developing the spacecraft, going into environmental testing, so that in early to mid 2022, the spacecraft will be ready to ship and ultimately launch sometime in mid 2022. We're designing for a 1-year mission, but I'm kind of hoping for longer. I want to quickly mention, this is, you know, Van Allen probes recently ended, and it can make a lot of people feel like radiation belt science is kind of taking a back seat now. But the next couple of years are going to be really, really interesting for radiation belts, due to kind of a boon of CubeSats and small satellites that I would say a lot of these kind of came out of the observations of Van Allen probes showing us what we needed to do next. So REAL is a CubeSat from Robin Millen at Dartmouth, which is going to make really those highly detailed pitch angle resolved measurements from low Earth orbit to better characterize precipitation. CERBI is not quite going to tie directly into what I've been talking about. It's mainly focused on inner radiation belt electrons rather than the outer radiation belt electrons. And Shinlin Lee is the PI. BOOMS is a balloon mission from John Sample, which again is going to do Bremsstrahlung X-ray measurements. And it's going to also image. So just like APEX is imaging precipitation from above, BOOMS is going to image it from below. GTOSat is a mission where Lauren Blum is the PI. This says Goddard, but she's actually recently moved to CU Boulder and is now faculty in the Astrophysics and Planetary Science Department. And GTOSat is the first CubeSat that's going to be flying through the radiation belts in a high inclination quasi Van Allen probes like orbit, a GTO orbit, in fact. And that'll be really interesting because a CubeSat surviving the high radiation environment of the radiation belts will be challenging. And then finally, kind of peripheral, I guess I'm just bragging here. Canvas is another mission that's coming around that we're developing here in the Aero department at CU. Canvas is largely developed by students, many of whom are on this seminar right now. And it's focusing on waves. its key focus is to measure VLF waves related to lightning and their effects on the radiation belts. But it'll also measure other wave modes, which tie into the source, the cause of this precipitation. So waves scatter the particles, which ultimately hit the atmosphere, and we'll be able to measure some of that wave activity. So that is all I have to say. I apologize for going a little bit over time. This is just my quick summary slide, which I don't think I need to read for you. I'll just, I guess, acknowledge support from NASA for this mission. I'm really excited by it and really excited to see how it comes along and gets built up. With that, I'll just say thank you all for your time and for listening.
Thank you. Are there any questions? You can either type them in the chat, or if you unmute, you can go ahead and ask.
I have a brief one, Nick, if that's okay.
Yes.
I'll keep the slides up.
Hey, well, thank you very much for that. I'm going to focus based on the engineering programmatic question. HAO is conducting a couple of concept study reports right now for some at the H-Tides 2020.
Yeah, due in a couple weeks, right?
Yeah, and we've noticed that the new guidance from Dan Moses is that there will be 3 key decision points: a SRR, a design review, and a flight readiness review administered by the Small Satellite Project Office. And my question is, have you had to go through those with your generation of H-Tides, or is that a new initiative on NASA's part for more oversight?
So I would, if I were you, I would double check the actual KDPs, because we do have 3 KDPs as well. But the KDPs we have were the pre-phase A, so that was our selection into the concept study. The second KDP was our selection into phase B. So we're past both of those KDPs. And then the third one is launch approval. And that's all they gave us as key decision points. So if they've updated it to include requirements review and design review, that's new this year. But I was looking at it because I'm helping with one of the ones at LASP, and I thought it was the same as last year, but I may not have read it carefully.
Thank you very much. Thanks.
So there is a question in the chat here from Dan Marsh. He says, thanks for the interesting talk. You show the highest maps from VLF. Will you be able to use that information in your inversions?
Oh, is that the H prime estimated maps? So he's talking about, got to go back pretty far. Did I skip it? I totally did. This one. Yeah, so the idea of this concept in this diagram is using VLF to estimate H prime. The H prime EST is estimated. We also estimate beta, so it's a 2-parameter fit to a D region density profile. We could include that in the inversion of the precipitating fluxes. So sort of combine the X-ray measurements and particle measurements in VLF. I think that probably a more realistic approach, at least early on, is to do them separately and compare what we get. So we are developing a method to use the VLF to estimate the ionosphere profile. That's a density profile. And then we can see how consistent that is with the precipitation that we estimate from APEX. I will add, though, that this is still concept. I've proposed this array to NSF, and I'm still waiting to hear back. So if any of you are reviewing it, you should say yes. Yep. Is that not kosher to, like, solicit from possible reviewers on a seminar?
Are there any other questions?
Professor Marshall, I have a question. A great talk, by the way. Yeah, hi. So most of the things are heritage for APEX, right? For things that are not heritage, like the instrument, for instance, how do you go about convincing them that this will work, especially when it's TRL 3 or below?
That's a really, So that's a great question. Thank you for asking that, because one of the things I wanted to highlight, but I kind of skipped over, the instrument is, as you point out, most of the stuff we're doing is fairly high TRL. When we propose a mission like this, we include a heritage table. It shows you the TRL of all the subsystems. And our TRL table said 999999994, where, you know, TRL 9 means it's flight proven, and TRL 4 means that we've kind of built it and taken some measurements. To be honest, that was a little bit of a stretch when I proposed it. My opinion is that these CubeSat missions, these science CubeSat missions for heliophysics or otherwise, they should be this way. They should be focusing on novel developments that have the potential for major impact. And I think that's true of APEX. It's challenging, of course, to develop the instrument, and it's taking longer than we expected. And I also mentioned that we proposed this 3 times. So in those first iterations, that was a big weakness, that the instrument was not proven and not ready. Over the years, as we kept getting rejections, we were actually developing the instrument and improving it and getting closer and closer to something that we could prove would work. So you might say that we were selected when we should have been and not earlier. So I'll also mention, you know, I don't remember if it was James Mason or Andrew Daher, but a couple of old CubeSat experts coming out of the aero department and LASP in the past. One of them said to me, with any CubeSat, you should do one thing that's really hard, and everything else should be easy. Now, as you know, working on the CubeSat projects, nothing that we're doing actually has turned out to be easy. But the idea is that we limit the number of really new novel things in the development. And so with APEX, that is really the instrument here. And everything else is, you know, heritage, really shouldn't be a showstopper. I kind of rambled, but I hope I addressed
no, that's fine. I was just wondering if there's a process from NASA or some other agency that you have to go through to prove that this will work, especially like proof of concept versus like a mock-up that works. And then, like, I know that it takes a long time, but like, are there like defined ways to do this?
They do. So there is actually something there, at least for larger missions, where NASA does actually have key decision points at PDR and CDR, where they'll decide whether you get to continue or not. With those missions, they would insist that the instrument is TRL 6 by preliminary design review. Now we're actually past preliminary design review and we're not TRL 6. So with CubeSats, there's a little bit of leeway. You know, CubeSats are trying to be rapid development. And so there are some liberties with kind of those restrictions. But as long as we can prove or show, or, you know, with reasonably high confidence that we have a path to success through preliminary data, through, you know, prototype instrument and so forth, you know, at that point, I think it becomes a qualitative decision from NASA. So I can't tell you right off the bat whether, you know, what's going to fly and what's not.
Yeah, no, that's a really interesting point you bring up. Thanks for clarifying that.
Sure.
Professor Marshall, I've got one. Hi, Arvind here.
Hi, Arvind.
I mean, this is out there, obviously, but is there any indication that this might work at a higher energy level for measuring maybe TGFs, the entire APEX concept, if you had similar detectors on board?
No, this detector could absolutely measure TGFs. TGFs, for those of you that aren't familiar with terrestrial gamma ray flashes, these are gamma ray bursts emitted by lightning, through in-cloud lightning, through processes that we don't completely understand yet. The TGFs they're often described as, you know, energies up to 20 MeV, but almost anything in X-ray and gamma ray, there's a spectrum, and that's the high end of the spectrum. The peak of the spectrum is actually in the energy range that this mission will measure, in the tens to hundreds of keV. So we could absolutely see TGFs. The problem is the time resolution. TGFs last for a millisecond, and our time resolution is a 10-second integration. So there's 4 orders of magnitude in time resolution that we don't have. One could conceivably redesign a mission like this. It would all be software to change the time resolution and set, sort of a triggering threshold in the data. So through software, this mission could be completely repurposed to measure TGFs. We would of course have to look at, is this the right instrument? Is this the right detector for TGF measurements? What science would we get out of it? Or would one want to design a mission with a different instrument? You got me going on this though, but I work a little bit with Nikolai Ostgaard, who is the PI of the X-ray detectors on ASIM. And that's a mission on the International Space Station that is specifically measuring TGFs. They've had a couple papers published from it already. And incidentally, it uses the exact same detectors. So that really highlights that, yes, these will work for TGFs.
Cool, thank you.
So there's one more question. I apologize if there's some background noise here. Quick here in the chat. So what's driving the offset solar panel design?
Oh yeah, the picture shown right here. That's a simple question. When they're stowed, we want one on the top and one on the bottom. It's much harder to stow 4 panels on the same face of the CubeSat. We only have a 10 millimeter space between the structure and the top of the solar panels when they're stowed. So 2 of them fold up and they sit on the top of the spacecraft, and the 2 of them fold up and sit on the bottom. But in the end, we want them both facing the same direction. And so that's why there's this sort of weird offset design.
All right. Seems like there's no more questions. So why don't we conclude there, and thanks again.
Yeah, thanks again to everybody for listening. And apologies again for going a little over time. Not the first time that's happened for me. And thanks, Nick, for hosting.